Hello, this is FlippedHarber for Precalculus. In this video we're going to talk about polar coordinates. The objectives for this lesson are to plot points in polar coordinates, convert from polar coordinates to rectangular coordinates, and to convert from rectangular coordinates to polar coordinates. The outline for this video, we'll talk about a basic polar system that consists of two things, what's referred to as a pole and a polar axis. We'll talk about what polar coordinates are. We'll look at finding several polar coordinates for a single point. We'll talk about what to do when polar coordinates are given where the r is less than 0, that is when it's negative. We'll look at plotting points using polar coordinates, and then we'll look at converting from polar to rectangular coordinates and from rectangular to polar coordinates. So, to talk about a basic polar system, let's start by looking at a simple XY system. You're very used to it. You're very used to plotting points given an x, y value. Now, the polar system, or a basic polar system, actually looks a lot like this, except there's some things missing. Basically, we have what we kind of look at as the positive x-axis, and that origin is what we refer to as the pole. So the pole is something that we revolve around, and the polar axis is where we start that revolution. So that positive x-axis is still 0 degrees or 0 radians. Now you really should probably think about this like a heading on a plane. If a plane wants to get from one airport to another, generally what they do is they take off and they know the direction that they should fly and they know how far they should fly. So that's really the way the polar system works. It involves a distance from the pole and a direction to get to that point, just like flying a plane. So polar coordinates are given as r, theta. That's a distance and then a direction. So the r basically stands for radius. It's a distance from the pole and the direction to get to that point from that positive x-axis that's now called the polar axis. The distances can be any number. They can be nice numbers like 1, 2, 3. They can be decimals. They can be fractions. They can be irrational numbers. They can even be negative. Now I know that sounds weird. A negative distance or a negative radius? Well, we'll talk about it. The direction is given relative to the polar axis. So 0 degrees or 0 radians would be the pole pointing straight to the right. 90 degrees would be pointing straight up. 180 degrees would be pointing straight left, so on and so forth. You should be very familiar with all of these angles. Now these are typically given in radians. Why? Well, because the math that happens is just easier when it's in radians. A positive angle means that you move counterclockwise from the polar axis. So think about that as spinning to the left. A negative angle then means going going clockwise. Now again, this is something that you're used to. You're used to 0 degrees being the x-axis and positive angles going up from there, negative angles going down from there. There are actually an infinite number of coordinates for the same point. If I give you a point in polar coordinates, you could give me an infinite list of different coordinates that get me to the exact same point. We'll talk about that. So let's talk about how to find several polar coordinates for a single point. So here is our first point that we've seen in polar coordinates. It's 2, pi over 4, meaning that it's 2 units away from the pole, the origin if you want to still call it that, and it's at an angle of pi over 4 radians from the polar axis, from that positive x-axis. So here we see it plotted out, 2 units from the pole at an angle of pi over 4. So again, it's like the plane is flying 2 miles at a given heading. Okay, so how do we give more polar coordinates for that same point? Well, one option would be to do a full revolution and then the angle of pi over 4. So that would be 2 pi plus pi over 4. Well, that gets you to the exact same thing. If you spin around once and then go to the angle, you're going to be facing the exact same direction. Well, another option would be to rotate around the other way, have a negative angle. So that would be a full revolution in the opposite direction, negative 8 pi plus that pi over 4. So again, different directions, different ways around will get us to the exact same point. Now we could keep going. We could revolve twice and then go pi over 4. We could revolve 3 times and then go pi over 4. We could spin around backwards 82 times and then pi over 4. So that's how we get all these different coordinates for the single point. Generally, we try, not always, but we try to have angles that are less than a full revolution and then a positive distance from the pole. Now, what if that distance is negative? Well, it can be a little tricky. I'll try to explain it the way that I think about it, and hopefully this works for you too. I think about it as walking backwards. So if I see a R value that's negative, I think, okay, I'm going to look in one direction, but I'm going to walk backwards to get to the point. So, you know, planes don't fly backwards, but I can walk backwards pretty easily. So -2 comma pi over 4. We still look in this direction here. Pi over 4 is still this angle right here. We're still looking in this direction, but we walk backwards too. So this point is over here somewhere. -2 basically means walk backwards too. So there's my point. Okay, now let's plot some points using polar coordinates. Here's another example. Again, 2 units at a direction of pi, meaning that we rotate halfway around the circle. So that point is straight to the left of the pole 2 units. 3 comma 13 pi over 4, well, here's one of those oddball angles because it's bigger than a full revolution. It's actually 13 pi over 4 is actually a little bit bigger than 12 pi over 4. 12 pi over 4 is 3 pi, so it's actually a revolution and a half, and then a little bit extra. Notice, now this might feel a little bit weird for you. These are both positive numbers, but it's down here in this, what we would normally call the third quadrant. You know, it just sets a direction to look. 13 pi over 4, a little bit bigger than 12 pi over 4. And then you go straight to the point, a positive radius. Here's one where we have that negative radius again. So we're looking in this direction here. We're looking 5 pi over 4, which is actually the same direction as 13 pi over 4. Kind of did that on purpose. But you walk backwards. Now again, this may seem a little bit weird. We see a negative number, but because of the direction that we're facing, that negative number ends up here where we're very used to seeing positive numbers only. Okay, so let's talk about converting from polar coordinates to rectangular coordinates, from r theta to xy. Well, we got a couple handy equations. Now, I'm not going to really bother you with how to find these. If you really stop and think about it, it's just the whole unit circle stuff, blah, blah, blah. But x equals r cosine theta. Y is equal to r sine theta. So if I give you the point r theta is equal to 2 pi over 4, and I'm just doing this as a reminder, you should pretty much know right away that this is polar coordinates because of this pi right here. I mean, it'd be really weird to have a y value in pi over 4, but I like to do this as a reminder. This is a polar coordinate. I want to change it into rectangular coordinates, into an xy. Well, all I do is plug 2 in for r, pi over 4 in for theta, do it in both of those little equations. I get 2 times the square root of 2 over 2, 2 times the square root of 2 over 2, and I get the square root of 2 comma the square root of 2. Not too bad. Now going the other way, if I want to convert from rectangular to polar coordinates, here again, a couple equations coming from all of our trig work. This should look very, very familiar, Pythagorean's theorem. And here we're solving for an angle, so we use an inverse trig function. So theta is equal to the tangent inverse, or arctangent, of y over x. So taking a point x comma y, negative 2.3 comma 0.2. Now these are really odd numbers. it really doesn't matter. Very, very few of these are going to work out nicely, and there's special cases that are going to work out nicely, and we're going to look at some special cases. But for the most part, this is not going to look pretty when it's in polar coordinates. Now I want to make a note here that this point is in the second quadrant. We go left and then up. It's in the second quadrant. So remember where your point is when you're converting to polar coordinates. So I go ahead and plug into my equation, or excuse me, plug into my equations. I'm solving for r. Now normally I like to work with a positive r. I actually have the choice here though with this square root. I can use plus or minus. There's reasons to use the negative. I like to work with the positive, you know. So r is 2.3. Now, this is a coincidence. Don't think that these numbers are always the same. This is absolutely totally a coincidence. Okay? It really has to do with the fact that this is so small. Now, if you stop and think about this, 2.3 at an angle of negative 0.087, this is a pretty small angle, and it's negative. That would put it in the fourth quadrant. Now, my original point was in the second quadrant, so this is like opposite where it should be. Well, it has to do with the fact that your calculator is only going to spit out a certain range of angles for this tangent inverse. This is why you make note of where your point is. Now, there's two ways to deal with this. I could make this my negative radius, but people tend to not like negative radiuses, so I'm going to deal with it a different way. I'm going to keep my positive radius, and I'm basically going to go pi plus this negative angle. What it's going to do is move it from that angle that's pointing down in the fourth quadrant, and it's going to find that angle that's pointing up in the second quadrant. So I get a polar coordinate of 2.3 comma 3.054, a little bit shy of pi, pointing straight to the left. Okay, so let's talk about some special cases. These are things that I want you to kind of recognize to avoid a whole lot of work for yourself. If you see r comma 0, doesn't matter what the r is, positive, negative, don't care. If you see r comma 0 or r comma pi, these points are on the x-axis. Are they on the left side or the right side? It kind of depends. Is that r positive or negative? If you see r comma pi over 2 or r comma 3 pi over 2, these points are on the y-axis. So if you recognize these special cases, you can save yourself a whole lot of work. The point 4 comma 0 is on the x-axis 4 units away from the pole. It's actually the point 4 comma 0 in rectangular coordinates also. The point 4 comma pi would be negative 4 comma 0. If you just recognize these special cases, you can save yourself some work. Okay, so that's it. There's actually going to be a second video for this section that you're going to need to watch. I'll have talked about that in class, so make sure you watch that video at the appropriate time. And I'll see you in class, and I'll see you online.